All right, welcome everyone to another Lambda 1 workshop. This is how it's going to work. First, I want to talk a little bit about what Lambda 1 is, really short. Then we're going to go through the workshop. So, welcome. We're Lambda 1. We're a community. We truly believe that the world's biggest challenges can be solved using the power of reason, technology, and collaboration. And that's why we're working really hard on empowering you, programmers. And this is why we're doing these workshops. So I hope you like our content. We're making a lot of efforts into making this bigger, into raising the bar of what are the skills of the common programmer, and that's it. So today our workshop is gonna be guided by Asen. He's our first member, besides me being the founder. And today we're gonna talk about side effects in pure FP. But before that, we like to start with this. So I like to say to people that we programmers are like philosophers, because one thing that we share with philosophers is that we try to extract the abstract structures of nature, right? As philosophers, one of the common activities of philosophers is to do ontologies, which are, concepts and meaning and relationship between that. But this is exactly what we do as programmers in order to do our programs, and especially on functional programming. We try to realize what are the abstract concepts of users, databases, or whatever, so that we can express them in code. So, this is not your common workshop. We actually are trying to create an experience which you're about to go through it. So please do think as much as possible, share your thoughts, and remember that there are no criticism, there is no intellect race, there is no ego, just curiosity and delight for the abstract. Okay? So we're here to be philosophers which find a lot of joy on abstract concepts. So we will apply a technique called the Feynman technique. So we will write down through the workshop what are our thoughts. You're gonna see how it's gonna work. Because we're trying to force you to reason, and this is really the key for you to learn something. So I would like to express that reasoning is really important, because in the same way that a martial artist would only go through the most difficult exercises through training their body, we as philosophers, we only dare to go through the most complex and difficult concepts if we train our minds. So we are trying to do that as well. This is why it's a workshop, because we're trying to invest into training our mind. If you don't get it right now, no worries, because you can get it given the right training. So that is introduction. And yeah, let me give the microphone and the stands to Asen Kolov, who's going to be guiding the theoretical session for today.
Okay, so let's get started. The topic is side effects in functional programming, and of course, why is that an issue at all? So let's start from the beginning. Functional programming is programming with functions, and what are functions? which is a question which we probably start many workshops with. What is a function? And so please really write down a sentence. How would you define a function? It's a question we have seen often.
Yeah, we do it a lot.
Are we supposed to write somewhere?
Yeah, in a
No,
computer,
like in a computer, just to formulate your thoughts
Okay,
instead of
not
in
some,
words. No, not to collect them on
GG's
paper.
Page or something.
No.
But that is the Lambda 1 model for workshops.
Yeah.
We stick to it.
Exactly. So the value really comes from trying to write it down.
And we may be philosophers or mathematicians, but we are above all programmers. So then on the next slide, maybe it's a bit too early for the next slide.
Yeah. First, we need to.
So let's. Zhenhao, what can you read? Can you tell us what you defined as? How you define the
function to
function?
me is something that always gives you a value when you receive the input. Assuming the input is according to the function specification.
Right.
You don't
Okay,
throw
great.
garbage to a function. No, okay.
Yeah. So you're a mathematician with a background in category theory. And maybe Mark, who is doing mostly JavaScript, will tell us his definition.
Function is a structure that, given some input, produces output.
Yeah, great. Let's see what a well-known programmer, developer, who is a big guru in the functional programming area, says about functions. So here's John de Gaulle's functions are, as what we said, they return an output. You give them an input, they return an output. But in this, there are three properties of the functions which are essential. And first of all, functions are total, so like they produce output for every input, and they don't throw an exception. They just let's stick to this. They return output. Secondly, they always return the same output, no matter how often you call them. If you give them the same input, they will give you the same output. And the third one is that the only effective running a function is computing the output. So there are no other things happening when you call a function. And so these three functions, this is total, being total, being deterministic, and being pure. They're something that give us a big power, the power to compose functions. And when we know what a function does, we don't have to go into the function, and we can replace every function with the output it gives us. If we have a function that produces something, we just use that something. And to be able of doing this, we need all these three characteristics. So side effects are something which has to do with the purity, with functions having to do only producing the output and nothing else besides it.
And before going to the next question, let's take 1 minute that after you've seen what we presented, please try to, if you want, to rewrite whatever you wrote, right? So, am I making clear? Yeah, okay. So 1 minute to rewrite whatever you, so even the added information or...
Hey, Rodolfo.
Welcome, Rodolfo.
I'm not sure if you mentioned this. That's the well-known technique Feynman technique of studying something. Just going through these steps first, writing your thoughts and then writing your thoughts again.
I don't fully agree with what John Go.
Yeah, tell us. No, of course.
No,
That
are we going to discuss later or?
No, it's good.
now is a good time.
Because like third point is that the only effect is the output. Well, like it's like again abstraction, right? It really depends on what you care because every function has side effect. Right? You go through computation, right? Generate some heat.
Yeah, great.
You change the physical world. I mean, this unavoidable. Right? Depending on how fast your computation is, sometimes you care. Or sometimes people say like a long computation is kind of side effect because of long latency. But it's fast, we don't care. Right? We say there's
No, great. I think it's not an easy question. What is the side effect?
Mm-hmm.
I think purity is about getting a value outside your codomain. You have a domain, and the function is a correspondence from the domain to the codomain that will give you an image, and the side effect is a value that doesn't belong to this codomain.
Like you increment a counter.
Or sign passes.
The scope of the function.
So heat is a value that lies outside the adding something to another something.
Yeah.
That goes from, so you are talking about the purity is not about really. If you go to higher philosophical ways of everything has a consequence, you can say that's fine. But the function is really a restriction over something to another something. A side effect is something that doesn't lie in this correspondence. You can think of the side effect as an output of a function, but still you get this as a tuple of things that go out, and your codomain just changes from one thing to two things.
So actually, we're at the next slide anyway, because that was the next slide.
An important thing probably to mention here is that we're trying to first limit ourselves to the world of a mathematical function, right? Not a function in our programming language, right? Or as a mechanism for computation, right? So, because this is what functional programming is all about taking the pure world of mathematics and trying to use it as a model of computation, right? So even though that maybe executing the function produces heat, and you could see it as a side effect, what we're trying to do is to model our programs through mathematics, right? And the important thing here about pure functions in a mathematical sense is that they enable us to reason by just thinking about the input and the output, because there is nothing else, right? You don't need to go into the function to see if the
you
function
cannot
is
go
not betraying you.
If it is a mathematical function, in mathematics, something is the way you define it. If it's defined this way, it is.
And if you are
So you
worried,
can't really go into
if you are worried about the heat it produces, build that into the function and go and say, okay, I have this extra input that is the processor I am in, the external temperature I am working on, and the
cost of computation.
Everything, you bring those in, and then you have the output of that function that includes how the function affected the world.
No. But what about logging then? What about logic? If you log a statement during your program execution,
Depends how you do
That's
it.
not
Do-
a side effect, actually.
is that a side effect or is that not a side
I
effect?
think it is.
Depending on how you do it.
Well, you don't write a function to log. Usually, if you do, it is not a side effect. But if you don't, logging is definitely a side effect.
It is definitely a side effect.
Yeah.
Oh, is it part of the output?
It is.
Then why is it a side effect?
Because you don't write function with intention to create logging entries. You write a function in order to add two numbers.
Yeah, exactly.
I'm inclined.
And if you can have it logging somewhere, then it added two numbers, but that's not the intention. You wrote a function.
Yeah.
Like there are things you care about and things you don't care about. Like temperature. When you write a program, you don't care that much about memory usage or temperature or electricity. Or you may say, I don't care that much about logging either. It's well, some physics of the implementation. It's not my problem. Yeah,
I
problem.
would say also like to add to your point, if something is not related to the input type of function or the return type of function, it's absolutely a side effect, right? If your input type and return type is not like log or logging, then yeah.
But that's the whole point of the going functional and the whole movement is like, wait a minute, make it important, because by hiding it, by pretending it's not happening, you get these weird bugs that you have trouble troubleshooting. So make it explicit.
So if things in your log may be bugs, like if your logs are interleaved with something which you don't want, if you can see that as a bug.
Sometimes you can't find a login backend, right? When you ship to the server, it says, okay, I can't find a login backend.
So maybe it's a good moment after that many examples, if we can define what is the criterion actually, when we can say this is a side effect and this is not side effect. Like we have an examples. Logging is not writing to the database probably is a side effect because you care what you wrote to the database.
For me,
Then let's write it down first.
okay, sure. Let's write it down.
And I see Hamid started writing.
Yeah. But still, so let's talk about this. First, we go from that the function is a relationship between a domain to another domain. That's
Right.
function. That's the mathematical expression that we want to say. So, but when you go inside computational domain, you have side effects. In a mathematical term, I don't think we have side effects, do we?
No.
So I'm just asking here, probably not. But if your signature, your relationship between an input to an output defines that there's going to be a log, then that's not a side effect.
There's going to be a log, like in the chance.
Logging.
Logging, right?
Logging,
Yeah.
sorry. So if you have logging in your output and the output defines that there's going to be a logging, then that's your domain model. Then it's going to be transparent. So you have transparency there. But if your domain model is defined, but it's going to be done something else to be done inside that relation, then it's a side effect. That's I guess.
When?
So basically, you have the relationship between the domains, but you are doing something else. Basically, I'm saying that your function lies about the input and output.
Yes.
Yeah, good.
This is really good. I completely agree.
Function lies about it's doing more than you can read from the signature.
Yeah, but
Actually.
but if your function does not lie and it still is going to even if the job of your function is not logging, but the signature defines that there's going to be a logging inside your function, that's actually a pure function.
Yeah, that's I think
basically, if your function is logging, basically function must be referentially transparent.
that's a nice word to mention. Referential transparency.
If your function is giving means kind of doing two things, now your function, are you able to replace that in a expression? Are you able to do that? If you are able to do that, then you can say it.
I'm a big fan of yours because actually I think that's the best definition of of what side effect is. And
So basically, when a function is referentially transparent, so you have the expression that many functions you can actually replace any time.
Yes.
It won't affect the
can
way it
replace
was.
value
Yeah,
for function.
exactly. Yeah. It won't affect that. But if you have two things, it may happen that it may log or system output.
And if something isn't referential
Referentially transparent.
transparent, then it's side effect, which is, for example, logging.
Which I think is
actually, that's exactly what I had prepared to say as a final truth. And I don't know. Well, there is where the final truth will come from. Actually, this is there was a huge discussion on Reddit about somebody asks what's wrong with future and why do I need pure handling side effects in pure functional way. And that one was one of the good statement of the author of FS2, I think. But at the end, when we talk about composing functions and being able to reason about functions, side effects are breaking referential transparency, and that's what makes it necessary to deal with it. And I'm not a very good presenter because actually I'm afraid I answered the question I had prepared for the next slide.
No, it's perfect. Probably we should take a time to rewrite what we thought side effects are. So let's rewrite.
And why?
The last definition, I need to take that into account. Because okay.
Yeah, I mean, one thing that we do in these workshops is that you don't have to agree, right? And it's especially good if you don't agree, because then you input something into the conversation, and you can write this down. Okay, so part of reasoning and part of being a community is to challenge ourselves, right? This is what is beautiful about mathematics, that you can deny some mathematician that died 100 years ago, right? And the community will accept it because you can actually write a formal proof of it. So yeah, let's use argumentation, reasoning, logic as our tool.
Okay.
I'm so sorry, I forgot your name. Oliver. We'll read what you have about this question.
Because of we were rewriting stuff. Why are side effects a concern? I think because it's not necessarily repeatable action.
Right.
So it's not important. So it can.
So repeatable, that comes to the determinism, probably.
It's the
like
problem of determinism. I'm manipulating something outside, and I don't know what it is. I can replace the function without achieving the same effect of the outside world.
Yeah, not being able to replace a function. Yeah, that's once again the referential transparency thing. And here is an example. If we don't look at this part, if we only look at this part, actually you can't answer the question. Yeah, are this expression and are this program and this program, are they the same program? If you just look at this, if you look at the Java code or JavaScript code, you can't be sure what it is, because you may guess it is if you say, well, it's a mathematical computation, like square or adding a number. You could think you could rewrite your program this way. But if you have like a name add to gauge, if the name tells you it's a side effect, you would never think of doing this, because the first one would add it twice and the second one would add it once. So referential transparency, that's the ability to replace function with its value, and you have a program which is the same. And if we allow our functions, well, I call it function, if you allow our programming functions to have side effects, we lose this ability. So that's why we need to do something to be able to handle side effects in a purely functional way. Once again, purely functional way means to be able to do these replacements always, like without any knowledge of how the program is implemented. Well, maybe with the knowledge that it's purely functional. Because programmer can always cheat. Programmer can always add a statement that does something nasty.
Let's pause there. Is this clear?
Do we have to read the left column and decide the bottom two rows confer with the top B?
So the left column is one program and the right column is another program.
Okay,
so actually, let's take the time to
actually this is one program.
Yeah.
And actually, this is definitely the same program. We renamed one function.
We're looking at the left column.
Yeah.
So given x equals is the outcome of f applied to a.
Yeah.
Given y is the outcome of f applied to a.
To the same a.
Y. Z equals x plus y divided by 2.
So this is one program. Let's say this is a program.
Okay.
The question is this program the same program as this program? If we had referential transparency, we could just use here instead of using, we do replacement substitutions.
I would say yes.
Well, it would be the same program if we can rely on referential transparency. If we allow to have side effects within our programs, we lose this ability. That's why we need a way to handle it. And apparently it has been quite difficult.
Do we have to make a distinction between side effects which affect the outcome of the function and side effects which do not affect the outcome of the function? Like logging does not affect the outcome of the function. So a function can be transparent.
Well, that is the thing, right? Like people say, like, why would I care about logging? And there is actually, like, for example, in Haskell, ways to just go around it for now. Like, let's not be pure on this one, just for the sake of logging because I just want to debug something. But probably, then again, logging is important, and this is something you want to have on production, correctly done, because otherwise you're not going to be able to trace things. So the important thing, and something that is going to become clearer next, is that you want logging to be part of your effect system or your handling effects, because you want to make sure that you are logging in the moments you want to log. So it is, I will say, it is important, at least for production grade code, to include log as a side effect that you want to handle. Just because you want to log whenever you want to log, right? You don't want to just skip it.
I think we.
The thing is, we are disregarding the thing because it doesn't really change the output. Like, if instead of being a logging, it's a transfer function. I'll take $100 from your account and give $100 for his account. But instead of just take $100 and give them $100, what I'll do, I will take $200 from you and still put $100 for him. So it's not that my function is you doing something that the output is the same. The side effect is really, my vision, is hiding something that should be clear.
Something you care about, actually.
The function defines the input is 5 times higher than the output. It can be referential transparent.
Yeah, but you say that, my function is multiplied by 5. But this multiplied by 5 do also write our own database.
And the question is it still referential transparent or not?
No, because you
the question, So, yes, the answer is no. It's not, because it is lying to you, right? It is doing something else than he promised to do, right? The type signature, and this is when we add types, right? Everything is about the type signature of our expressions. So if one effect of the computation goes beyond the type signature, then it is breaking that transparency, right?
And it is something you program against. If, for example, if you try it to the database, it's not like dissipating heat or something that happens by you care about what's written in the database. If you happen to not care, like a very hypothetical situation.
Yeah. The thing is, it's not about getting the functional and change for an expression, but getting an expression, can I change to this function and it works perfectly. So if I
Without thinking, like blindly.
If I have a x times 5, and now I get this multiplied by 5, and that doesn't have like a IO, I cannot do a printer and something, it will break. But the signature is the same. So it needs to be both ways, not just from the function to the expression, but from the expression to the function.
Yeah, they must be freely replaceable.
We'll do an exercise on which actually shows itself in the end. Yeah.
What is the next slide? Yeah, and well, the same. We are used to do side effects with features very often because it happens because side effects often are getting something from the outside world. They are slow, so we are used to composing to do this within future.
At least on the Scala.
Yeah, in the Scala world, then it is quite typical Java program. Well, a Scala program, the way to organize futures, and apparently. This program is not the same program as this program because let's imagine that future, it adds to gauge. Actually, the moment we create this value, it will start doing the job even before we started using it. And in this case, we'll add to gauge one time. This thing is going to add to gauge 2 times. Just the small side remarks. We are used to do this with futures, and futures are no good if we care about referential transparency. And, okay. We've said that many times. We want referential transparency, so that's why we don't want side effects.
Let's do reflect about this. So is it clear why side effects are actually a concern?
Well, initially I made the difference between innocent side effects as side effects that only write a log, an entry to a log, or heat. But side effects can also have graver consequences, and you cannot make a distinction between side effects that have grave consequences and side effects that have not. So we say side effects are a concern. Does that sum up?
Yeah. Honestly, I actually categorize them innocent and non-innocent. So I also do that as a understand.
I mean, but logging can also not be innocent, right? Let's say that this is full.
Yeah.
Okay.
What happens then to the computation?
Okay.
If it's a blocking clause.
Yeah, absolutely.
Oh.
Yeah, there is like logging trying to debug something, and then you remove the logging in 10 minutes. Or you're deploying some production system where you care about your logs being precise.
It's difficult to reason about your code. That's something I came up with as well, and makes sense.
So when we say difficult to reason about our code, how do we interpret that statement? What do we actually understand out of it? That I want to understand what others think about it. What do we mean by reason about our code?
Well, I would say if it's easy to reason about code, you can say this function always returns this output given a certain input. And it becomes difficult when, for example, you have something else than just adding 2 numbers, which does or might have a consequence on the output. That makes it difficult because you do not know what this other process is, and you do not know when and if it will have consequences. That's
good.
You can also say there's like, among other 2 key positions when you're reasoning about equational reasoning. For example, this says you can substitute, right? That there's referential transparency, and you can substitute functions by their eventual values, or that you can assume associativity and these types of laws will hold. So we thinking equationally about things. There's no surprises. So it's like, oh, I was totally surprised by what this did. That side, and then also the local reasoning side, which happens to be that, oh, I don't have to actually look inside the function to see if it has side effects or not, or if it'll work this time or not. It's like I can think about what the local body without having to worry about the rest of the environment.
And adding to that, this actually backtracks to our last meetup, our last workshop in which we talked about controlling complexity, right? The big problem that our code becomes spaghetti code. But why? Because there are too many parts that depend on each other, and our mind is very limited. There are so many parts we can hold on our mind, and that is complexity, many parts, right? And what a pure function allows us is to completely offload a bunch of conceptual things out of our mind. Because if a function is purely determined by the input and output, everything inside the function we can upload it of our mind, and that is massive, right? Because then it becomes really easy to just say, I have an API, I don't care how it is implemented, I only know it does blah. Right?
You even don't need an API, you need a signature.
Yeah.
Literally, at my work, last month I saw a program which is called for two-factor authentication. There is a method called check if location is unknown. I don't know, maybe it returns the boolean or something. And literally, it also sends an email or SMS.
If it cannot, it will not return a boolean, but
no, it will return false, but in the meantime, it would also, not an email, but an SMS. It would also send an SMS to the well, there is a way to organize code better even without going purely functional, but if you were purely functional, it wouldn't happen because this thing would have returned an IO, and then it wouldn't be a boolean.
Either in a non-mathematical or in a non-concept or a layman, what I used to understand is like, when I write code without even compiling, without even testing, my brain can think and compile and say, oh, this will function, this combination of functions will give me this output. So actually, that is kind of a reasoning. But if we are able to do that and the compiler is going to do the same thing, that means we are able to reason about the code.
Yeah, great. That's sort of the golden rule of what it is all about. Let's go back to the. If we have these things, we can freely compose. Otherwise, we cannot compose. So we know why it is a concern, and the question is how to solve this. And as a totally side note, I think it's really been a very difficult problem because when has it been solved for the first time? I don't know exactly the year, but then it has been introduced in Haskell. You know which year? 1990 or something?
A long time ago.
Excuse me?
96 or 99, I can't remember.
96, 99, yeah. I would say something relatively recent, and so let's not pretend we can figure out how to do it and look how it has been done. It's been done in this clever way, applying these two things, these two techniques. First of all, we cannot exclude side effects because all programs we do, we need to interact with the world. Our program has to print something, it has to read something, and to write to the database. Otherwise, well, it's clear. It's not a program we will be paid money for to write. And so we have to do this, but we can describe the side effect. We can describe what we want to do instead of doing it. And while describing what we want to do, we can compose these descriptions. We can do this in a purely functional way. Let's go ahead with it.
Is excluding a post request an example of a side effect?
Yes, definitely. Oh yeah.
Because every time it changes the output, the thing posted is every time different.
Yeah, even I get.
Or it's not idempotent.
I would say post is definitely a side effect because it can transfer money by way of speaking. Well, post is intended to
give an input, money, the output is always the same, that money.
Yeah, but it's not. It's a post request. Yeah, it's a network request. So basically, the next time you don't have a network connection, it doesn't return anything.
Yeah.
Which is true about the
It's
get.
not transparent.
The most important thing probably is that there are side effects involved in the process of actually doing it, right?
Yeah.
Like, for example, starting a connection. Starting a connection is completely a side effect, right?
Yes. Oh yeah.
Yeah.
So
It's
you
very
don't-
if you fail when the connection doesn't exist.
Mhm.
That means it's not even a function. Because sometimes you return a value, sometimes it doesn't.
You can
So-
reason about
Yeah, exactly.
function that doesn't host.
And besides, you write code, and suddenly you need some infrastructure around you to be running. Even if it is local, if it never starts, if you read from a local database and it will never fail, still you have to start the database, and it's
So how do we make it pure?
we will try to do this, to separate the description from the execution, and then in the end, at one point in time, when we have done all our programming, we'll say, go for it and do all the things I have described.
End the world.
End of the world.
Common call.
And here is once again a question. So we have talked a bit in our meetups about functors and monads and applicative functors, and yeah, if you don't know these words, it's not a bad thing. And but if you happen to know these things, so if we try to model our description of the description of the things we want to execute, if we want to model this description, what type of structure do we need? And well, the idea is that functor is something that has a map. You can change something which is inside the description. And then Coyoneda, I don't know exactly what it is.
Yeah,
Maybe Jekyll knows. But the essence of the monad is
That's the Placely? Is it Placely?
No.
Coyoneda.
It's very
It's a
seldomly
theorem.
referred to as a structure. It's kind of you can think of Coyonera as an extension, so a functor with extra properties that lets you compose a functor into a monad.
Okay.
Yeah.
that's well, it's not the topic here. The Dubi it says you make anything to a functor with a Coyonera, and that's how Dubi says. I need a functor, so
there's a lemma that allows you to build a monad from any functor. That's your Neda lemma. So all you need is something that has map, and then you can build a monad on top of it. So you can get pure and flat map for free from anything that's a functor.
great.
There's been further work, but anyways.
No, thanks a lot. Actually, the goal of this sentence was to throw in a few difficult words. Actually, I chose something which I didn't know what was meaning. But so if a functor is something with a map, the essence of the monad is that if you have some, it allows you to continue. It allows you to compute something in a context, like make an I/O, and then based on the result of this I/O to make another I/O. And
Chain functions.
yeah, chain executions. Absolutely, that's exactly what monad is. So,
I think probably the only thing that you should know is that functor is a programming pattern to decouple context from computation. Okay, and a monad is just a way to combine these things in a sequence way. So just like functions compose, these context with computation, you can also combine them in a sequence way. So yeah, in this case, this functor, which is gonna be I/O, it's simply gonna decouple or side effects from pure computations, which is or business logic.
Apparently, there is something called Yoneda as well. This is called.
No, the Yoneda.
Yeah.
So
Yeah.
you need the Yoneda and Co-Yoneda to end up building the free monad in mathematical sense. But yeah.
by the way, an unrelated pitch I think on 14th of January is the next meetup of the category theory study group, And the topic of the next meetup is the Koyuneda lemma. Yoneda lemma or Koyuneda lemma. I'm not sure about that because good. So we,
It's the name of the mathematician.
Yeah.
It's a person's name.
Yeah.
right.
Ko is from one
Yeah,
has a
yeah.
dual. Yeah. From the,
Yeah, in category everything has a co. Every worker has a coworker. Yeah. And, but for this meetup, everybody will have watched Bartosz Milewski's. We have read Bartosz Milewski's description, and we are going to discuss it. So I think I will be able to talk about the Koyuneda on 15th of January, but not today. The idea is we want to have a description, and we want to be able to change those descriptions to get what one description produces to describe the next step. And for this we need a monad. And monad, the way monads are described mostly in Scala, is well, if you have a flat ops, what was that? If you had a flat map, which is exactly is it correct to say the continuation thing or the sequencing thing?
Sequencing, yeah.
The sequencing. And if we have anything that has those functions, so why am I looking at the screen? Sorry. That has this and this, it allows us to put something in an I/O, and then if we have this method, this is what makes a monad. And shall we read what exactly it means? The flat map.
Sure.
So if okay, so we describe a computation. So we have a method. We want an I/O which will return us something, like read from the database and return us an integer, or read from the console, read from the console and give us the string, like read line. Read line would be a function, and if we want to describe an I/O that will return us a string, we will provide a function that will actually run something and give us what we need, and that's how we will make such an I/O, like describing. And this is, in fact, this is this. We provide a function which, when run, executes. You don't know the Scala syntax, but this is a way of saying this is a function. This is completely like a Scala JavaScript. No, it's not fat actually. I made it fat for to look fancy. The fat means nothing.
Yeah. So that R, if you say apply a R and then the fat arrow a, that when there's this fat arrow in the argument of a function in Scala, it just means make it lazy. So it's not going to evaluate that a until you explicitly need it.
Like providing a function in JavaScript.
It's called call by name.
Mm-hmm.
Yeah, it's called by name. But that's what we need. And let's see how actually this is the signature. Imagine we had such a thread that was able to run something and give us a result. And if we had this thing, can we implement a flat map? It is a known fact. If you can implement a flat map, you can implement map in terms of flat map. So this is actually the only difficulty, how to implement the flat map. And let's go for it. So you have an I/O that returns an A, and you have a function that takes this A and returns an I/O of B, and we need to return this I/O of B. And well, that's, let's say, the only way of implementing this function. We want to construct a new I/O. That means we have to provide a new run function. And this run function will run this method. First, it will get the read line. It will get this. It will give it to F, which will give us a new I/O, and well, then this run will be running this run. Maybe, well, it's just a code. Does it make sense to explain the code? But does it sort of make sense? Well, it makes perfect sense for the Scala developers, of course. But I guess it makes some sense for the non-Scala people.
So to rephrase, so first of all, well, just to explain the technicalities of Scala, this trait is an abstract type, right? So whatever, right? This has this def run abstract function. So when you create a new object, you need to implement it. Now this function is gonna hold the side effect, okay? So it is a non-pure function, which once you run it, it's gonna unleash a side effect, right? Now what we want to do is contain it, right? The whole strategy of an IO is to always hold the function that is gonna unleash the beast, right? Now, what we want to do is in flatmap, for example, is to create a new so first, let's look at the signature, right? It says given an give me a function
Like
that given an builds a new IO. Okay.
Like
so,
if you have a string and you print the string, let's say.
No. Okay. So yeah. So for example, let's say that
Or you have a user ID and you get a user from the database.
yeah.
Right, yeah.
So this A comes from the run function in that IO, in that object, right? So
You can think of it as a user ID.
So the idea is creating a new IO with a new function that first runs the first IO to get the A, and then pass it to this function to get the second one.
Okay, and it's lazy because you only want it to run when the second function triggers it.
At the end of the world.
If you
When
see
they do run.
if you see the new you result into a new IO B, which has its own function run. Then when you execute it, it executes the run of the inner IOs.
Yes. Okay.
So if you see, we're still holding the side effects. We're still, and this is the whole thing of delaying the side effects.
Yes. Okay. It's a separate function.
And by the way, if you probably don't know this syntax either, but this actually it's this reverse arrow. It's a flat map.
Okay.
So this thing means it chains this IO. You can read it as IO. Then this is the run method, and then it says dot flat map, the value you obtain from here, which is non-essential value, with this IO. And then dot flat map, once again, what this IO returns, it's called name, and then it calls it flat map with this IO. It's another way to...
Yeah, the same idea is famously called do notation in Haskell. Because you see the sequencing, right? So do this, then that, and then you get the result available to you on the left side. See that name is a result of readline. So
okay. So it's these are like change functions.
Yes,
exactly. That's
Okay.
the most correct term.
Brush up on my Haskell knowledge.
So Oliver, are you very familiar with this, or is it? Okay.
Yeah, this is why we say that monads are sequencing with context, right? So these flat maps or with the for or do notation, it's actually just function composition, but which carries effects and compose them together. Make sure that everything is nicely threaded.
Yes.
And actually, in fact, if there were not some practical considerations, that would be a perfectly good monad implementation, and we could write huge problems with it. And how did we solve the problem? We can say, well, we didn't completely solve it, but we did this suspend and delay execution. So we describe in the run method what to do, and we do execution at the end, which is wrong error. And we call run here at the end, which is here. So we do all the compositions. They may be much more complicated than that, of course, but we never do run. We do run at the end. And maybe even you use something that calls run for you, don't call the run. And this program is pure. Well, it could have been a good place for a slide to show that this is referentially transparent. But there are problems with this implementation. And it is if we go this, like, let's try to implement the Fibonacci sequence. Well, we've implemented something for side effects, but it doesn't have to go to be a side effect. Our run can be something simple. We can provide like a value, a ready value. If we go this way, we are going to call flat map, and Flat map is going to call Fibonacci, and it is going to call flat map, and it's going to call each other, so we will get a stack overflow. So this will work for like 20 or 200, and, but it doesn't work for for bigger numbers. Well, stack overflow, and functional programming does a few really clever things. Oh.
Can you go back?
Yes. I ran this to make sure it works, so I think it's good.
How many cycles?
But, excuse me?
How many cycles?
How many? Very fast, like with 100,000 breaks in less than a second. Like press the enter and it breaks.
This is not related to I/O.
No, it's related to our implementation. If it is our I/O, but our implementation, we believe it will be good to work with side effects. But even if we, even if it works with something as simple as a function returning a number without going to the outside world, it would break.
And theoretically, it's correct. It's just the fact that behind the scenes, there's a computer with a stack.
It works with a stack, yeah.
That runs out. It could be a computer that has no fan, and eventually it can also overheat. If the number is too high, then it generated too much heat and it crashes.
So if we were mathematicians, we would say, well, that's it. Let's go home. No problems. every problem. So. Yeah, Zhenhao, what to do?
No, okay.
So let's say we start with.
You're trying to define a.
Yeah, first it starts with these two defaults. If we want to calculate, for example, for 3, then it would call IO of 2, which is this plus 2.
He's trying to make it tail recursive, if that matters to anybody.
No, it's not tail recursive.
This is not tail recursive. That's what we want to do actually, to make it tail recursive.
That actually is tail recursive.
No, it's not tail recursive because we call this FIP. Wow.
It's at the end of the call.
Yeah, it's with the if, it's with the end.
No, but
That's not the problem.
It is not that recursive because the expression needs to return in order to compute flat map.
Exactly. It's in flat map. So it's
That's true. That's
Yeah, flat map could do other computations. So yeah.
Actually,
so fib, I think you annotate fib with tail recursive, and it is, but so fib is tail recursive. It, however, lives in an environment or executes an environment that is not.
you mean
That'll
like
go,
the other function?
With tail rec, it should compile.
Because
Anybody
FIB,
try that?
well, FIB, that's tail position, indeed.
It is in the tail position, so it is tail recursive in that sense.
But it is not the last thing it does. The last thing it does is compute flat map.
exactly. So that's a boxing layer.
Exactly.
Yeah.
But
It's
would
boxed.
it compile really? Because it's actually it is not tail recursive because it is within a function, with another function, not within. I'm not confident about that.
Oh yeah, of course. Yeah, I'm silly me. That's not tail recursive. You're right. Because of what you said, it pretends to be, but it is inside a.
So let's make it tail recursive, which is quite hard actually. I think. And also extremely smart, because while doing it, you discover how you make a lot of other things tail recursive. And so the problems with this implementation, first of all, the stack overflow, but besides we can't handle concurrency, asynchronous things, and we have no control at all about the running. Yeah, we just start something and wait it to finish. We call run. That's all we can do. So it is not really a good implementation, and it will take a bit longer to make one. So the next thing is calling this flat map function recursively calls this stack overflow. So that's not what we want to do. So let's the technique used to this is once again describe what we want to do. The book where anywhere this turns out to be called church encoding, like a side note, for each function which you want to call, you define
Data type.
a data type. Thanks a lot. And it's not something I deeply understand, the church encoding, but well, that should be the gist of it. Doing something like this. So what do we want to do in our I/O? First of all, we want, of course, to be able to return to return values, which give us this data type or maybe a function call we want to do, and then we want to suspend calls, like to say we want to execute this, and well, it's called suspend here, and once again we need to be able to flat map. And we just here put the data which we need to do this. If we want to return something, we put the data which we want to return, or what we want to execute, and here we want to run to flat map on one I/O, because that's the sequencing, the chaining thing, and here's the method. That's all that we do. And given these things, we can, once again, we implement map in terms of flat map and return. And our flat map, well, that's all. What can we do with this, actually? Do you want to add something? Because I'm not sure what's on the next slide.
The important
What's missing?
Run.
Yeah, we need to run this thing. Yeah, we can't describe any computation, and at the end we need to be able to run it.
But the important thing here is that what we're doing right now is moving calling functions, and instead of calling functions, we're putting them into data structures. So this is why we say suspend the computation, because instead of continuing the computation, what we do is we say no, wait. We're in functional programming. Functions are as good as code is as good as data, right? So we're gonna take our function and put it into a data structure, and that will wait there until the moment I need it again, right?
Isn't it the same, Francisco, as what we were doing here, for example, when we were constructing here? We didn't call it suspend, but yeah, here we just.
This is very similar, except that when we do it with data types, we're more expressive, right?
Yeah.
In here we have more verbs.
So there you see where at the flat map declaration, the run is still just that raw sequence of running. So you are unrolling, so you're pulling out the self. That self is pulled out immediately in the run. So there's a chain of pullouts.
Yeah.
Right, so you'll keep all this in memory, but there's a chain of pullouts that never escapes the stack.
Yeah, exactly.
Exactly. Yeah.
I was more thinking about this suspension. That, like, when you just say suspend, it is like the same as this pure. Well, it is not the same actually, because you don't put it inside. You define. Yeah.
Yes, but pure does not exist afterwards. So it's at the end of the world, whenever the final run is called, you are never escaping the stack.
We are always going through this.
It's always inside a stack frame and then you call F, and then you pull out, but then you call. There's no breathe. The stack gets exhausted.
Every flat map goes one deeper.
Rodolfo is definitely saying the key thing here. Just to complement it, when we put it into a case class, in this case, or just a class, what we're doing is creating an object, and so what we're doing is jumping to the heap, right? So now we're trampolining between the stack and the heap.
At every suspend.
Each time we do flat
that's why
map,
we call it suspend, right? It gets suspended into the heap.
That you can't see because run is missing.
No, return is there, right? You have the return. That's the run same thing. I think so.
but we can describe everything we want to do, but we cannot run it yet. Here's the trick how to run it. That would be nice to hear this. So if you want to run it, actually here is the easy case. How do we run something which is a suspended computation. We just run the suspended computation, something that has a value. We just return the value. And here comes the trick. What about flat map, which is the difficult, what causes problem that calls another function. So here that's the technique. Here's if we match on the IO of the flat map, because flat map contains one IO and one function from what is inside the IO to another IO. So there are, once again, there are two easy cases. Like if this IO is a return, we can just run, F, this is the A, this will be another IO. We can just run because we have an IO. What about stack? Why don't we go deeper in the stack here? So we are calling run. Oh, because that's a tail position, is it?
No, well, not specifically because of that, but because, for example, when we say, let's say we run, right? And the first one is a flat map, so it's case flat map, right? Yeah. And then we extract it from the data structure, right? And then let's say the next one is also flat map. Then when we run it again, it's putting the result. We will jump into let me see. We will jump into that flat map, and it will go back into encapsulating it into a data structure, right? So it is jumping between putting the result of the computation in this data structure and then executing it here, and then going back here, and then going back here, and going back here, going back here.
I'm leaving. It's getting too deep for me, but the introduction was really good. Thanks, and probably see you next.
Yeah, that would be great.
Thanks. Bye.
And actually, that one has a separate name. It's called the free monad.
Yeah, which is two slides further.
I know. But
Thanks.
You were so close to the free monad. And the great trick here is, of course, when you have a flat map to flat map, that you can rewrite this, moving the flat map to the right, never having one flat map within another flat map. So, which is when this X is a flat map. So, when you have a flat map of a flat map, so this thing is this flat map. So the trivial implementation would have been what would be the trivial implementation? As here we run. Oh, sorry, I'm lost. We rewrite this. I can't write down the trivial implementation right now. What would it have been anyway?
But, yeah, but let's move on.
Yeah, let's move on. I'm losing time on try. Yeah.
But anyway, like if you take time to like analyze this on your home, you'll see that first through the I/O we're actually declaring our program, and then this run function is actually executing it. So this is the clear separation between declaring your program and doing composition, and then from actually running it. So yeah, if you analyze it at home, I'm pretty sure you'll get it with them.
Yeah, definitely. If you write it out, and actually this string, the last monad associativity law, the best way is just to blindly copy it over, because it works great. You just look at how it is defined, and then you replace what you would trivially write to the associativity law, and that's what it comes out of it. And what about our I/O? Well, in this case, if we rewrite our example with the futures, we just have either this program or this program, and they will be the same program because we will have two IOs, and when we go to running, they will be run two times, either being written this way or being written this way, which is the same thing. It's a value of something. And let's move further. And I suggest really not go deep into this at all. Just a small observation that what we wrote has nothing to do with I/O. That actually we found something smart.
Just some monad.
Yeah, we found something smart that can chain computations without the stack overflowing the stack. So it is maybe a tail recursion class, we could call it. And in this class, if we go,
Yeah, so the reason it's called the free monad, the free part is that it has no extra properties other than the minimum you need.
it's free of interpretation. It is monad that just has a flat map.
It only has what you need to do map and flat map. And there is no other extra stuff like I/O, which will handle exceptions, or future that does caching. So in the previous example, you don't have that those extra rules that because it's Scala's future, then it caches the solution, so it's smart and doesn't run it. The free monad doesn't have any of that. You can add them if you want. Whenever you're going to write your interpreter, whenever you're going to write a run, you can cheat in this run and make that other program break referential transparency if you want.
Yes. But here we have a monad that is just monad and nothing more. It can chain
so
chain
it's the
things.
free one, and then you can add on top of it whatever you want.
The observation here is that if we just replace, here we were returning, if we go, it is exactly the same. This trait called async is exactly the same as was I/O a few slides ago. And here we were returning an A, but say instead of A we return something like parallel computation or something which after we call it, it will start the computation later, or any other thing. And if we make this observation that these functions are the same, we can notice that we describe with this thing, which is the free monad, that we can describe both I/O literally if we replace this F here, either with function returning something or with whatever else. It is the free monad, which is a great observation. Great observation. And I think that's all that we have before we start with the exercises. And with all this, that's how we could write our programs from now on. If we use some implementation like cats. Let's start with the exercises, Francisco.
All right. So I'll take over for the second part, which is actually trying to code something. So did you guys set up some Scala environment with Cats effect? What we're gonna see. So in this case, we're gonna use Scala to show all of these ideas, and we're gonna do it. Scala has some libraries made by the community which implements it. There's two very popular ones. There's Cats and Scala Set. In this case, it's Scala Set I/O and Cats effect. In this case, we're gonna use Cats effect for no particular reason. You should check both. They are both based on the same theory, but they have some key differences. They're mostly the same. So, first of all, this is how a program. Yeah. Let's go to presentation mode. Enter presentation mode. Thank you for that. So,
And make the font a little bigger if you can.
the font bigger? I don't know if that's possible in presentation mode. Sorry? Yeah. All right. So anyway, so we said with IOs we like to take the actual execution of our program and delay it all the way to the end, right? So with these libraries, you could do the .run in the end or use a run function in the end, but these libraries actually bring you a runtime environment that will do it for you in a more optimized way. And actually, if you go to the pure world of Haskell, in Haskell you have IOs by default, and if you see the main function in Haskell it returns an IO, just like this finish function here. And the runtime of Haskell will actually execute things for you. So in the end, as programmers, we only need to care about composing our functions, and the runtime will actually care about the actual execution. Just as a disclaimer, if you're well, not a disclaimer, but if you're a Scala developer, this environment has actually becoming more and more popular. There's a lot of libraries being based on this, like for example, HTTP4S is a great HTTP library that is based on Cat's effect, right? Or Doobie for database integration, and all of these libraries, they really integrate nicely because they follow these abstractions all together, right? So first, if you're ready, I'm gonna program, and if you have your environment, probably you'd like to start copying this program. I'm gonna show you how to first suspend a side effect into our IO, right? So we create a function, and let's go for the simplest one. So we're gonna print a string. What we're gonna do is return an IO of unit, right? Actually, as a side note, unit, if you have a function that returns unit in general, or void in Java, it is the type signature of a side effect, right? Because it's either doing a side effect or absolutely doing nothing, right? Which is silly. So,
That's not a side effect. You can do nothing and it still appear in the pure function.
Yeah, but that's why that's why I'm saying it's either doing nothing or a side effect. So exclusive for. So so in this case, units, let's say, represent our side effect, and it's inside an IO, right? So we're actually delaying the side effect. So how do we do it? Well, specifically in Cat's effect, there is a function called not suspend, delay, which is gonna take a computation, print line 8. It's gonna take a computation and actually take it as a lazy evaluated expression and suspend it into the IO, as we saw in the beginning. Of course, that's a really good idea. So delay takes a body, and as we saw, this arrow called by name thingy, it's actually only making it lazy, and it's putting it into the data structure as a lazy evaluated. Actually, I think it transforms it into a function that receives nothing and returns the value. So, voila, a pure print. Why is it a pure print?
It's referentially transparent.
It's referential, and why?
Because it doesn't do anything.
Because because it's not doing anything. It's just creating a data structure, right? This is a data structure. Creating a data structure is a pure computation, right? So now we can actually run our code. Let's try it out. So I'm gonna make here a for comprehension, returning the exit code success, and we're gonna print Hola Mundo. Well, I'm Mexican, so my first hello worlds were actually Hola Mundos. So if we go not to this one, but this one, and we go to SBT, and then we run it, Now, do you know how to lock a thread? So just lock in time in Scala, or actually also Java.
Right? Thread.sleep.
Yeah, thread.sleep. Is that a side effect? Is blocking a side effect?
I would say.
Yeah, it is.
Okay, good. We're gonna use it in a moment. So first, we're gonna run this and see if it runs.
During IntelliJ, weren't you? Why not running from IntelliJ?
I don't know. I really
Okay.
like my
You like
terminals.
command line. Okay.
Yeah. And voila, hola mundo. Now, first exercise, make a function that purely locks the thread. So blocks for a couple of seconds. The function that does that is throw.sleep, and then there's some milliseconds inside. So let's say 1,000 milliseconds. That function is from the Java API. It blocks for that amount of time. So please make a function that does this, but in a purely functional way. If you would like some help, please let me know. Which one is my beer?
Oh, come on. Why?
Probably that one.
This one.
Yeah.
Just one for you. Yeah, this. I
Okay.
really don't know.
Okay, doesn't matter.
Oh, let's.
Yeah, you share some of my. Tell me if you're ready. Raise your hand if you're ready. Man, Rodolfo is programming his phone. No?
Are you?
Yes. Before I was just on the text editor, but
Oh, come on, you are using Scala Fido
of course, why not?
in the cell phone. You're a lawyer. Rodolfo is my hero.
So actually, who wants to finish this? Someone which is not Rodolfo, who wants to finish this type signature? Okay, IO. Why IO of unit? Yeah, it's a side effect, right? And we want to suspend it into the IO, right? So it is, and this is why we say in functional program type functional programming that we take our side effects into the type signature, right? Because then it is clear that this function is meant to do side effects because it takes IO into consideration, right? And when you want to do something with it, you need to consider that. So you need to compose those IO. So let's actually implement it. So what is the next thing? What is the next step? IO what?
I just applied it. What does apply
apply is actually a synonym nickname alias of delay. So delay and apply is the same. So it is the same doing IO of something here or doing dot delay. But let's just keep to the concept. Do delay. And then we'll have the expression that makes the side effect inside. So thread.sleep for minutes. All right. So, are there any questions on this? Is it clear? Okay. Now let's actually use it, right? Let's, for example, go and print hola mundo, then sleep for, let's go for 3 seconds, and then print hello world. Okay. Now we'll run it. And bam, right? Our side effects were executed in the order we wanted. Now, what is one of the, one question?
Well, in this composition, what is the difference from calling IO delay or IO pure?
Or IO what?
Pure.
Pure?
Pure.
Ah, pure. That's a really good question. IO pure is the way in which we take a pure value, so non-side effect, into the IO, okay? IO.delay makes sure that the side effect doesn't get unleashed, right?
One takes it in by value, one takes it in by name.
Yeah. And
pure takes it in by value, so if it was a function, it gets executed before it goes into IO.
That's why in this composition, what would be the difference?
So, for example, if we do IO.pure, it wouldn't work. The side effect would.
Well, it would work also.
Would not work now. Well,
on the line where you make the value.
So this is the problem. Pure, as soon as pure does not do call by name, it doesn't do it lazily. So as soon as we put the side effect full expression in it, it will first call the side effect and then put it into pure, which is definitely not the order we want, right? So that breaks referential transparency. So, and we have pure because this also helps with what is the word when you want it to run fast?
optimization.
Yeah, well, it helps for optimization. So performance. That's what I was looking for. So it helps for performance. Because if you have some pure computation, some pure value, it is easier just to shove it in, and than a side effect that you actually want to have it in the right data structure with the right laziness and blah blah blah. But
That's interesting. I was thinking this is like two different things. You're right. It's just for performance. You can always do
In fact,
delay.
the pure is about materialized value, and the delay is a non-released value.
Yeah, but it is
You
not
are about to realize.
yeah.
But
then
the pure is
yeah.
about materialized value always. So it's the monad when you apply something into it is about materializing something into a monad or something like that. Delay is just okay. My materialized value is something that will be computed after, but it's something that we say we describe this way, not the mathematical works around it.
Yeah.
Can you make it pure and just run it? I want to see the order.
So in this case, it's gonna work, but why? Because actually, for example, if we do some side effects, like for example here, so
It should actually. No,
Make a
it
function
should actually
sleep 3000.
sleep for 3 seconds before it prints hola mundo.
Yeah.
So actually, let's do what Asen did in his slides, right? We do or we're gonna do our program dev program, and
That also will be or you could call it 20 times the sleep.
so, yeah.
The thing is, when the focal page will open, it will run the sleep as it should have. So the call position in this case.
So let's do this. So we have val program program one dot io dot pure for example print line one hola, and then we'll have val program 2 io dot delay print line hola dos, and we're gonna do first. Let's do P1 P1. Okay, so if we run this, how many holas are we gonna see? Any guess? Bet you make your bets now.
Which one was it? I don't remember.
How many holas are we gonna see?
One?
Oh, one, definitely one.
1, 10 on 1.
Definitely
One.
Yeah.
20 euros on 1.
Oh, that's expensive.
Okay.
Well,
Anyone
actually,
wants
we're
to bet on
We're
2?
going to see both, but one outside complication and one inside.
What?
We are going to see both because, well.
Are you sure? Are you ready?
Yes, we are going to see two.
I'm sure it's one.
Yeah, I'm sure it's two.
1.
Why?
One?
Why? Why? Why?
Because it's unit. It's not a unit. You
Yeah.
call it once, you pass unit to pure.
Yes.
So that's it.
Oh, but you call P1 only. I thought you were calling P1 and P2. Come on.
No. So let's now call P2 and P2.
Illustrate your program.
Now, why do we see that first hola?
You pass the value
Outside
to the
of the
pure.
loop.
So when we evaluated P1, so when
If you put a lazy, it won't show.
Nobody wanted it to show, and poof, there it was.
there is a moment in which we evaluated this expression
It will
here,
show.
and
Yeah.
so once again, delay engages or side effects. Pure doesn't. Okay.
Isn't it? Maybe I think.
All right. Any questions?
I
No?
think you should always call pure with the pure value instead of setting stuff.
Yeah.
Yeah.
So
That's why it's called pure, right?
yeah,
You're
then
not supposed to do this.
the name helps a lot.
Yeah.
But still, it's easy to make
The pure it is taken from the whole model laws. It's coming from the model law that you have a materialized value.
Yeah. Pure is not strictly only part of IO. That is true. Pure is part of, in general, monads, right? Every monad has pure and flat map, right? Pure has different names. It has a unit. It's also called as unit. It's also called pure. It's also in Haskell. It's called, you know how it's called in Haskell? Return. It is
Point.
return. And point is part of the monad. Wait, the monad class is return or point?
In Haskell, it's return. In
Yeah.
Cats, I've seen points and view.
Yeah. So it has different names, but it's the same function. It does the same. And so it is return in Haskell, whatever. And then flat map also has different names, right? There's flat map, there's bind, there's the funny cool symbol. But yeah.
the thing is that there's no difference in fact from pure delay. It's just as he said, is a optimization not to spend time trying to find the value, just grab the value and use it. But they are almost the same in the mathematical function.
Now, I want to move forward. So, because I really want to show one of the coolest things about doing this, because this is not just about being obsessed about side effects or controlling exactly when they're executed, but we gain a lot from the fact that we just made only a blueprint of the side effects, right? And that is that since they're still not executed, we can add semantics to it, and that is awesome. This allows us to add concurrency and parallelism to it, right? For free. Because we have a program which represents an I/O, and then we say, we can execute this several times if you want in parallel, or they might share some resources or whatever. So because these are purely blueprints, they haven't been executed, so we're safe. So let's see, for example, what Katz effect brings into the table. One of the things that we can do with Katz effect is, for example, let's first take our program. Let's call it just P, right? We're gonna do this. So we're gonna use our nice print function here. So let's print one cat, and then we have this funny looking symbol. I'm gonna explain what it is in a moment. So this star, then more than, is actually just a synonym for flat map, which just ignores the incoming first argument, right? So this is the same than doing this dot flat map and then ignore, right? So just to make it more readable, and this is what we gain from functional programming, type function programming, is that our programs become more readable. This can be changed for this. So that is nice. It becomes almost as you're reading English, right? Sorry? Oh, fuck, thank you. Delay. Thank you, that was a good catch. Now, let's see what concurrency and parallelism verbs we gain for free from Katz effect. We have, for example, let's make a list of programs. Let's do a list of our repeated program. Let's put it 3 times, okay? Then, since I'm doing import Katz implicit.everything, this adds certain methods to list, given the right circumstances, and we can do par sequence. What do you think this does? Yeah, well, par comes from parallel. So we're automatically parallelizing it. So let's see. So what do you think is going to be the output of this? Yeah. So let's
given the right execution context.
Let's go. Let's think how could we do that without I/O if we were programming like C-Java, we have a function.
Yeah, it wouldn't be that straightforward, right? Because what we're doing here is decoupling everything, right? So since we were able to decouple expressing our program from the actual execution, we were able to really easily add extra verbs to it, right? So this is great because, for example, P can come from a library, and then you can add all the parallelism and that you want to add, right? So that is great. We can actually see where parse sequence comes from. So this is something that we can study later, but this is a method injection, or what is it called? Pimp my library, whatever. Yeah, well, it is type class. It's using type classes, but this is a way of injecting methods to something that follows this pattern. So if you have some higher kinded T with some higher kinded M inside, in which case T is list and M is IO with something inside, then we can inject this parse sequence, given that the T on the outside has an instance of the type class traverse, and the M has an instance of the type class monad, and there is an instance of a parallel between them both, and then bam, you gain this for free, right? So great. We just gain a lot of parallelism verbs for free. Now let's see another thing that we can do. Actually, do you guys want to type down?
Excuse me, what was the question?
Actually, do you guys want to type down? Actually, let's make another exercise. Make a function that receives a program and executes it in parallel for a provided n times. I don't know if this makes sense, but the type signature looks like this. Def so what will be the type signature? First, we would receive a program. So in this case, what does a program mean?
I of something.
An IO of something, right? So A.
Why not a list?
Because you're receiving F.
Oh, okay.
Yeah.
And then let's see, receive an N, and then you'll finish this type signature, but make a program that will in parallel execute. Make a function that will in parallel execute this program n times. Yeah.
Into a list.
Yeah, actually, we hide it a little bit what parse sequence returns, but it actually returns an IO of a list of the results, right? So, okay, we'll see some insights in a moment, but let's. If anyone wants some help, please let me know. So I'm gonna start, unless someone wants some extra time, I'm gonna start coding something here. So please speak now before your naiveness becomes spoiled. What is it called when a child is small and you know he cannot realize the harsh truths of it's naiveness, right? Like you think everything is beautiful and then suddenly you get broken. Innocence, innocence. Like
Last moments of innocence.
yeah. So let's see. So what are we gonna return here? All right, awesome, right? So we get a program, the amount of times we want to parallelize it, and then we return an IO of the list of the results, basically, right? So, all right. Then again, why is it an IO that we're returning?
I know why inspection matters.
Yeah, no. We're just describing, right, the parallelization process, but we're still not executing it. Yeah. So let's see. First, we already saw that on a list of effects we can call par sequence. So list has a really nice method already, I think, which is repeat, fill. Yeah, so fill, then n times with program, and this will create a list with as many IOs as n. And then from here we can say par sequence, right? Bam, done. That's how straightforward it is in functional programming. Isn't that amazing? So now we can try it out. Let's go for all in par of p. Let's go for 5 times. So we'll run it. This is the program. Did you guys were able to reach something like this? Good. So let's see the result. And it's, well, we didn't see the time inside, but yeah, so cat, burp, burp. All right, great. And as a final example, before our final words, I would like to show another example of adding extra semantics to our delayed programs, and that is racing things, right? For example, IO has a function here called race. Okay. If you see, race takes 2 IOs and it returns an IO of either. right? So it basically returns either left with the result of the left one if it won the race, or right with the result of the right one because that one is the one that won the race, right? So let's actually just try to raise these two, which are practically the same. Now, what do you think is gonna happen? Let's actually parameterize this one. So def p, and then let's just call it yeah, animal. That's a good one. This returns an IO unit. So this is our animal, and then p with cat, and p with kitten.
Catch is constructed first. No, but that's pure chance.
Yeah, I don't know. I guess also pure chance. I probably it depends on how it is implemented.
Yeah, let's put somebody.
It's. I will say that it's gonna be cat, but
Oh, that's good observation.
no, but let's actually take the result and go and say prints the winner, right? String. A, what is A? A is either either unit or unit, right? So we'll probably want to do this. Does it?
I mean, your animal signature is wrong, isn't it?
Ah, yeah, you're right. Yeah. Okay, let's see it. So, well, this is the function, and we'll see. I say cat is gonna win just because it has to execute something. I don't know. I don't know.
Oh, you have to try
Uh-oh.
one more time.
No.
Oh, this is.
Oh, you kitten one. Yeah. Yeah, this is extremely random, right? Like maybe this is how we could, we could add randomness by picking the random number inside an IO, right? So that randomness is maybe, contained as a side effect as well, and try it out. But I will suggest you to play with this at home, and to start closing this. Well, first of all, are there any questions? No?
So what if something fails? What's the error?
That's a really good question. So IO has actually an error handling mechanism. You can do this. IO dot raise error, and it takes a throwable, like for example new exception.
You could do that in your delay.
But one thing that you need to take into account, IO raise returns anything that comes first, if it's an error or not. So if an error comes first, this is the one that you.
Yeah. So it short circuits like an either. So there is ways to improve the. Okay, so let's go super fast through this. Yes, if your side effect throws an exception, this will come out as a failed IO. If you're familiar with futures, it's very similar, right? Now, the nice thing is that you could check if an IO is failed and do something about it by doing something like, for example, dot recover or dot attempt. Dot attempt is really nice because it returns an IO of either throwable or fail, right? So are your two options. So you could do say attempt and then for example, map, right? And then yeah, do case left and case right, and then map both of them into the same type and blah blah. This actually IO has an instance to monitor error with the left one being throwable. If you don't like to fail into throwables because you say, hey, this is basically just throwing exceptions, then you can make it an bifunctor and check actually the IO from Scala set, which is by default a bifunctor, which means it's like either. It has two types as arguments. And the IO of Scala set has the first type as the error type and the second one as the returning type. So it's like the fusion of either and IO, right? So yeah, check it out. Actually, what you should really check out is the documentation pages of these libraries. Specifically, Cat's Effect has improved a lot its documentation. It's this one. It even has a tutorial in which you go through the main concepts. It adds a lot of type classes and extra utilities that you can have based on all of this. For example, all of these concepts on concurrency and all of these type classes if you want to generalize on stuff, etc. So really, really, really nice and useful things. There's this concept of fiber, which is green threading, which is threads which are not on the operating system level, but it is actually on the application level. So it is threads that you can with your program manage and therefore become more efficient. Very lightweight, so you can have a lot of concurrent operations. But I'm talking, I think, hundreds of thousands, if not millions or something like this, with a really, really cheap. So it becomes really nice to do all of these operations. Very efficient, very expressive, very controllable. It's really nice. This maps perfectly well to Haskell. In Haskell, all of this comes out of the box. And for example, if you're into front-end even, this is a strategy of Elm. Elm provides you with an API that describes the program, and then the runtime of Elm will make sure that everything executes as accordingly. So all your Elm code is actually pure. And this is a general strategy that you could use to make a framework, for example. Maybe make the new akka actors, which are actually well done and not a freaking chaos. But anyway, I think this in general wraps it up. If you don't mind, on the very end, I would like to take a picture. If you do mind, no worries. And we at Lambda 1, we want to make this bigger. If you like the experience, we want to replicate it. We want to make it bigger. We want to influence the industry. We want for you guys to actually apply this at your work and have lots of fun. So please, you can support us by coming to our events. And we also have a Patreon page in which each type of crowdfunding in which we can accept monthly donations from people. And please also follow us on, we have Twitter and we have this application called Discord, which is for chatting and video chatting. So you can stay connected with us on what we're doing, because we're not just doing the workshops, we're also doing open software, free software. And our projects are really cool. So if you want to be connected with, some nice pure functional programming projects that you want to learn from, then that is also a great place to be. And finally, we also want to start helping you guys get nicely positioned into nice works, in which either you can apply all of this, or in which you can function as a evangelist, exactly. So So if you're in if you want us to help you get positioned, please contact us in lambda1.io. There's a email there, and please, anything else, we're trying to create a community, so everything is welcome. And thank you for coming.
Catch my bus if you take the picture. No.
Yeah, let's do it.